Okay, in this lesson, what we're going to do is we're going to concentrate on mechanical energy, and we're going to look at something called the work energy theorem. Before we go anywhere, we should review what potential energy is and what kinetic energy is. So potential energy is stored energy. And I want you to think of an example here. If you were sitting at your desk and somebody sat above you and they had a brick and they held it above your head, you might be able to picture that could do some damage if somebody dropped that brick. Now, what types of things are important about the brick? Well, the bigger the brick, the more damage it would do, and probably the higher you held the brick, the more damage it could do. So if we got a bigger brick and we put it up higher, we could say that the potential is there to do more work. Now, we have not dropped the brick yet. This is just energy that's being held there. So if somebody has their hand on that brick and they're holding it up there, the potential energy of that brick is equal to the mass of that brick times gravity, which is going to allow that to fall on your head, times the height that it's at. So this is the formula for potential energy. Okay, this may be review, and if it is, that's great. It's always good to take a look at this. Let's look at another example of potential energy. If I was going to have a campfire and I had a bunch of logs out ready to go, I might look at those logs and I might say to myself, wow, this is going to be a really good fire. It's going to be really hot. There's going to be a lot of energy coming off of it. Excuse my artwork. There's no fire going yet, but the potential is there for a good fire. The more fuel we put on the fire, the bigger the fire can be. But at this moment, the fire is not burning. There is just the potential for that fire. So kinetic energy is energy in action. So let's go back to our same old examples. There you are sitting at a seat. Somebody drops that brick and now it's moving. Those are motion lines, believe it or not. Now that brick is moving down. How much energy kinetic does it have? Well, the energy it has is based on the mass of the brick and the velocity at which it's moving. So this is the energy here when we have no motion. Everything is just waiting to go. The energy here would be based on the velocity. Now, we are only working with mechanical energy in this section. We're not going to work on thermal energy, but we can imagine the things we would measure once we lit those logs on fire. Okay, so we could measure the temperature coming off of those logs to tell us a little bit about the kinetic energy or the energy in action. This is looking at a system before anything's going on and thinking to myself, I wonder how much energy's here. This is where that energy's actually being released. Now, here's something that's interesting, and this is from the last lesson. Energy's conserved. So if we know the amount of energy potential we have here, we know the kinetic energy right before it strikes this person's head. Okay, so energy is not lost in systems. It can be transferred to other forms like sound and light, but it is not lost. Let's try and take a look at the work energy theorem and see if we can do a simple problem. So the work in a system is equal to the change in energy in a system. That is the work energy theorem. Remember, the definition of work can be found in the term energy and vice versa. So these two terms are interchangeable. So what we want to take a look at here is the amount of work that has occurred. We're going to take energy final minus energy initial. Now, we must give the car a mass. Let's give it 100 kilograms. So what we have to do is look at the energy final. So it is moving, so we can use the kinetic energy formula. We have 100 kilograms times 20 squared because it's moving at 20 meters per second. And then what we do is we subtract the energy initial. So the energy initial, the car has the same mass, it's just moving at a different speed. So what we would do here is we would square 20 and we would times that by 100 and get 40,000, and we would multiply that by half and we would get 20,000. And here what we would have is we would have 100 times 100 is 10,000 times a half is 5,000. So the work done is 15,000 joules. Okay, so this is a small section. Section 2 is a small section. U3A2, sorry, assignment 2. Activity 2 is a small activity. And basically what you have to do is you have to make sure that you understand kinetic energy, you understand potential energy, and you have to understand that work is just the change of energy that occurs in a system.